This episode begins in a bath. You probably heard the story behind the Archimedes Principle.
Archimedes is climbing into the bath trying to think of a scientific test to determine whether or not a goldsmith had used pure gold when he made the king's crown. When he came up with a solution, he was so excited that he jumped out of the bath and ran through the streets of Syracuse naked, screaming, "Eureka!"
Archimedes' Principle is something to get excited about. Without it, we couldn't float hundreds of thousands of tons of steel on the surface of the ocean. But I'm getting ahead of myself. What exactly does the Archimedes Principle say?
Any object wholly or partially immersed in a fluid is buoyed up by a force equal to the weight of the fluid displaced by the object.
In other words, fluids push objects up with what's called the buoyant force. And the buoyant force is always equal to the weight of the fluid that the object crowds out. The opposite is true too.
As soon as the forces acting on an object become balanced, they'll cancel each other out and the object will hold still. When it comes to objects suspended in a fluid, this state of equilibrium is called neutral buoyancy.
Take this Zorb, for example.
As you can see, it isn't accelerating up or down, so it's neutrally buoyant. The buoyant force pushing up is equal to the gravitational force pulling down. The Zorb is displacing a volume of water that weighs exactly as much as the Zorb and I combined. And that's the trick. You just need to displace water up to this line to create an upward buoyant force equal to the downward gravitational force.
If we could force the Zorb deeper into the water like this beach ball, the forces would become imbalanced until we let it go. Then it would accelerate upward until it came to rest in a neutrally buoyant position. But here's an important point of clarification. Archimedes' Principle says that objects in a fluid are buoyed up by a force equal to the weight of the fluid displaced by the object.
A bowling ball displaces about 10 pounds of water, so gravity beats the buoyant force in the battle over this 12-pound ball, while this 10-pound ball displaces just enough to stay afloat.
So far, we've looked at things that float to the top or sink to the bottom. But what about the middle? Can things be neutrally buoyant there? Sure, submarines, scuba divers, fish. Lots of things are neutrally buoyant below the water. How does that work? Let's look at scuba divers.
They wear what's called a buoyancy compensation device, or BCD. This is basically an inflatable life preserver. When a diver wants to increase the buoyant force acting on him, he taps a button to inflate the BCD with compressed air from his tank.
The diver doesn't lose weight when he does this, he's just moving air from one part of his gear to another.
But when that air is free to expand in the BCD, it displaces more water, the buoyant force increases, and the diver floats upward until the buoyant and gravitational forces acting on him neutralize each other.
Then, if the diver wants to go back down, he just lets some of that air out.
Though he does lose the very small weight of those bubbles, a deflated BCD displaces much less water, so the diver becomes negatively buoyant and he sinks until the forces balance out again.
That's it for this episode. A big shout out to Utah Bubble Sports for letting us use their Zorbs. You'll find a link to their site along with more science and research opportunities for BYU undergrads in the description below.